We were discussing about dynamic management of power by how we can do that by scheduling the voltage at different levels. And I think in the last class we were with this diagram where we had shown that there is a limit to which you can go with the area with a trade off between the processors, number of cores and the amount of cache memory. However, I cannot explore this entire space because of the requirement or the constraint of the power. So, because of power, I will have to restrict myself. Say power has been predicted to be should not be more than 130 watts, which will be difficult to vent out. So, therefore, we will have to restrict ourselves to a particular zone of so much cache and so much processor. All right. Therefore, many paths are not accessible, many space that was a possibility is not accessible. And later we had shown that even by voltage scaling, we can go beyond this space and can explore this space, but because of the bandwidth issue, we will have to come to an optimal which is around 44 processors around this point. Okay. So far we had done. Next, what we will discuss today is about what is that? Dynamic power management. Okay. Dynamic power management it works like this. There, instead of a single processing state that we usually have, the operating system schedules it from the ready queue to the processing state, etc. Now, that processing state can also be divided into multiple states. For example, there be a run state, there be an idle state, and there be a sleep state. Run state is normally operational, okay? And let us assume that at run state it is consuming a power of 400 milliwatt. Now, there are points when the CPU is not exactly running, but is waiting for some event to occur. So, till then the processor can remain idle and I can switch to the idle state, and I said I can switch to the idle state. Who am I here? The operating system. The operating system will switch it to the idle state and say in idle state it will consume 50 milliwatt power. And whenever there is a software routine or some event that calls for the processing, then there will be a wake up from return from the idle state to the run state again. And this there is a typical delay of say 10 microsecond to go to the idle mode and 10 microsecond to return from this idle mode to this mode. Okay. Here the processor was not actually doing much, but was monitoring the interrupts and all those things. But there may be cases when we really do not do, we want to shut it down. At that point of time, we can go from here to the sleep mode or also from here to the sleep mode. So, in the sleep mode it is a shutdown of the on chip activity. Okay. But the power is retained, it is not the power off that when our machine goes to hibernation. Okay. the processing is not consuming any power, but the the power is kept in the bank, I mean in the power supply, right. So, suppose that takes 90 microsecond. So, here also 90 microsecond. Now, when from sleep I again start working, then I will have to return again to the run state, and that takes around 160 millisecond. Okay. So, typically say, so if the operating system, depending on the task scenario, can switch between these states, I will be certainly in sleep I am actually consuming 160 microwatt, all right, much less. Where from is this microwatt coming? I mean, always we have talked about that equation, that power equation that we had talked about, the that is equal to the alpha CL V dt square F, right. Now, that was talking of the switching power, but as we are having more and more transistors, then there is a leakage current, and leakage power actually is also not insignificant. So, those are being consumed anyway, and the operating system will have to do this. Now, it is an open issue that how it can be a nice thing to study as to what would be the best algorithm to find out how we have to predict, because you see each of these transitions are consuming some time. Therefore, if I often send it to the sleep mode, then waking up from the sleep mode is taking 160 milliseconds. That may not always be affordable. Okay. So, this is another way we can carry out the management of power. This is known as dynamic power management. There are issues in this as well, where the algorithms which have been proposed, I am not going into those algorithms in detail. Now, given this, we have looked at the power aspect. Now, the problems that we are interested in, we know that we want to minimize or optimize on energy. We want to optimize on maybe code efficiency. Okay. Now, these are also related to each other. Whenever, if I can make the code efficient, if I take less amount of code space, then obviously I will be running the program at an early time. I mean, I will be completing it at an early time. Therefore, the total amount of energy that will be consumed is less. Another point also you should think of, when a program is running, where are the power points, I mean, where does the power get consumed? Is it only in the CPU? In CPU, of course, whenever I am computing, depending on the number of cycles that operation takes, power is consumed. Power is consumed also a heavy segment during memory access. Memory access, the more access to memory we do, the more power we consume. Therefore, another relevant thing, if possible, we will see later, is that how much can we reduce the access to the primary memory. If you can keep most of the data in the registers in the CPU or in the cache, in that case probably those memory references can be reduced. Next, what we will see now is another way of minimizing energy. Look at this slide. if I carry out parallel operations, okay, at low voltage, what was our problem? What was our problem when we did voltage scaling? Our problem was that we had some deadline, we had to meet that, and for that we had to run it at a particular frequency, and in order that we can run it at a particular frequency, we had to give a particular voltage. And as we gave a higher voltage, we could reduce the time, and with higher voltage we consumed quadratically more power. Now, what if I now go towards parallel execution? Okay. Let us look here. Our typical equations tell us that power is proportional to the supply square of the supply voltage. The frequency is proportional to the supply voltage. Okay. The energy is equal to power times time. Run time is assumed to be fixed here, and T is proportional to 1f. Now, suppose I had to do a particular number of operations. Now, I start doing parallel processing, and instead of doing one instruction per clock or one operation per clock, I decide on doing beta operations per clock. Okay. I am doing beta operations per clock. Then my effective clock frequency gets reduced to f prime, which is f by beta. Okay. Similarly, the voltage is reduced to, I can therefore, since it is linearly dependent, think about the tau equation. Tau was k times VDD by VDD by V threshold square. Therefore, ultimately it becomes proportional, the frequency. So, if I reduce the VDD, as I reduce the frequency, I can reduce the VDD. Okay. More delay I am allowing. Then the power for parallel processing will be whatever P I was assuming here, whatever power I was getting here, divided by B square per operation, because VDD has been reduced and the power is proportional to the VDD. Agreed? So, power for beta blocks will be, this is, so the power is being divided, power is proportional to VDD, VD square, right. Now, we are reducing VDD to VDD by some scale beta. Therefore, my reduced power, this is also, if that be the reduced power, that will be P by beta square, right. And therefore, for all the, this is for one operation. So, for all the operations, beta operations will be beta times this, and that will be therefore P by beta. Okay. Time is remaining the same, I cannot change the time will have to do the same. Therefore, the energy requirement will be, again, this was P prime times T is equal to E by B beta. No. What is the time? The time that is told over here is the time, worst case execution time of the programs. All right. I have to run it for so much time. Earlier, I was running at a higher voltage. I am now running at a lower voltage. That is the only change I am doing. I am not shrinking the time here. So, that is, this certainly, if I look at the slide again, this certainly puts up an argument in favor of voltage scaling and parallel processing done together. I can do parallel processing, and along with that I can do voltage scaling. So, that is another way, that is another architectural way of dealing with power. I will now talk about two other things which some of you might know in your some advanced architecture class, that is very long instruction words. Where instead of having one instruction, I will have my instruction will have a large number of instructions. Here I am showing 4 instructions in one instruction word. You know that the instructions are kept in the memory and the program counter points to a particular memory location and that particular instruction is fetched, decoded, executed. Now, when it is being fetched, instead of fetching one instruction, if I can have 4 instructions, for example, taken at a time, then what do I gain? Number of no, I am not taking from disks, I am taking them from the RAM. So, disk 6 are not reduced, but number of memory accesses are reduced. So, assume here I have done some calculation mistake, it should be equal, all right. So, forget about, suppose it is here, this is gone, this is nothing, all right. So, up to this is my instruction word. Now, here suppose I have got my instruction 1, here is instruction 2, as here is instruction 3 and here is instruction 4. Suppose I have taken 4 instructions. Now, there are further advantages that suppose so therefore, I can now take the help of parallel processing, because suppose this one is coming to a floating point. Suppose this instruction is a floating point instruction. So, it is coming to a floating point unit, all right. This one is coming to an integer unit. Integer unit, all right. This one may be another integer unit. Integer unit means it is just doing the integer operation. So, I am assuming that my processing space is divided into identifiable and functionally independent components, and here is something, say memory unit, memory access is being done here, some memory access. So, therefore, what happens is I can, when I fetch one instruction and I can carry out 4 operations in parallel, right. I am decoding and all those things. Now, relatively we have seen that will be consuming the for decoding the combinational circuit will be run, that consumes less power than memory accesses. Okay. So, now how do we find out? Say I am putting it 4 such independent instructions and clubbing them together. How do you know that when I have written a program like this, these are the 4 or 5 instructions or 6 instructions, which of these can run independently? Say this instruction is reading A, all right, and this instruction is say taking A times 5 and putting it somewhere else. Therefore, these two are not independent, right. Therefore, I can put in this way only the instructions which are independent. The task of finding these parallelly executable instructions is given to the compiler. the compiler actually finds the parallelism. It is moved from the hardware, the task is moved from the hardware to the compiler, and therefore, ideally this will avoid the energy, it will usage, unnecessary energy usage. But this left much to be desired. I mean, there were a lot of expectations which could not be directly fulfilled, because it was giving us low code efficiency. For example, suppose I do not have a floating point operation here. In my this code, I do not have a floating point operation, but in my instruction sequence there is a floating point space. So, I have to fill up, I means again now here what is I? The compiler. The compiler will fill it, will have to fill it up this part as a no op, all right. So, this will have to fill up with a no op, no operation, and therefore, often lot of space is wasted and we get low code efficiency in terms of the number of, I mean, I want to reduce the size of the code. So, that also always does not happen to that extent, but to some extent it certainly pays off, and this is another architectural move to reduce the power. Okay.
Are these slots prefixed to the floating point unit?
By the instruction set, yes. The instruction set has got certain floating point, some structure, and we have to fit it up. We will have to put the instructions there. Okay. Now, one very popular, this is being used EPIC stands for explicitly parallel instruction code, which was used by TMS, very popular DSP chip 320 CX, C6 and C6 series was there. What it does is very interesting. It keeps one bit to encode the end of parallel execution. Like, say I have got 32, I mean each of these have got 32 bits, each field is having 0 to 31, and here again like that I have. So, and here is the 31st bit of this, the 0th bit of this, like that, 31st bit, 0th bit, 31st bit, 0th bit. Now, the LSB of each of the instruction words, this is the LSB of each instruction word, is either 0 or 1. I am doing it wrong way. I hope you understand. This is not the LSB is always being kept at 0 or 1. All right. Suppose I make it 0. Now, if it is a 0, that means the next instruction will not be executed in parallel. Okay. Suppose now I have got instructions are A, B, C, D, At the end of instruction A, I put a 0. At the end of instruction B, I put a 1. At the end of instruction C, I put a 1. At the end of instruction D, I put a 0. At the end of instruction E, I put a 1. F, I put a 1, and G, I put a 0. These are the LSBs of each instruction. All right. Then how will for the different cycles, if I draw here the cycle versus the execution of the instructions. In cycle 1, what will be executed? A will be executed. And because A is not being executed in parallel with, this one is not being executed in parallel. But when I come to B in the cycle 2, B says that let C be executed in parallel with me. C will be executed in parallel. C says let D be executed in parallel with me. D says no. Cycle 3 starts with E. E will be executed and E says that let F be executed in parallel with me. F says let G be executed in parallel with me, and G says no. So, you see EPIC is a little modification of or extension of VLIW, and that is how the embedded system designers or computer designers, if you ever work on some chip design or instruction set design, this shows how innovative people can become to design new types of architectures. The architectures of a computer system is nothing but mostly the instruction set design that you do. Okay. So, this also helps in parallelism for reducing the time, as well as it is saving in the memory access by allowing us to fetch more and more instructions at a time. So, next let us see, here we will try to show. In the last class we had said that
we had fetched only 4 instructions in EPIC, but the example which you gave was for 8 instructions. Suppose the last instruction.
I have not drawn all those things here. I did not draw all the instructions, I had just shown, I had drawn only 4 here. All right. Here I have drawn only 4, but actually these 8 should be drawn here. Okay.
Is it a fixed number, like how many instructions?
That depends on the architectures. That depends on the architectures. How many, how wide is your instruction word? Accordingly, you can predicate that. This is known as, say, this 0 and 1 that I have put in as a single bit is a sort of predicated thing. We will soon see the ARM how we can compress the instructions in a much better way. Okay.
And the last instruction, can it have the last bit as 1? The last instruction.
What would that mean? 1 means, see, 1 means the the next instruction should be executed in parallel. Now, for the last instruction there is no next instruction, therefore, that 1 will not mean anything, right. So, here you see how we said that our happy point is somewhere here, happy island. I said that we want to reach somewhere near the efficiency of ASICs as regards the number of operations per joule, the power density. So, we can try to do that by different means, by changing the compiler, by having some other code tricks. Normally, we can proceed towards, we are approaching towards this close to power efficiency of silicon. The power efficiency of silicon is this curve. So, this one we had discussed in the last class, that tenfold increase of power requirement for mobile phones generation after generation. Now, let us look at where does the power go in a particular mobile phone. Is it only in processing? where is it? It is this pie chart shows you that around 30% power is consumed in the modem and the amplifier. Okay. Application processors are taking 20%, memory takes 20%, color display and backlighting that we use 10%, audio codec and amplifiers 10%, other peripherals are taking 10%. Therefore, although RF is a major consuming thing, and we all of us know that that is taking more power, but others are also not less guilty. They are also taking power. It is not that only this RF and networking is taking power. Your color, smartphones, styles and all those things are consuming power. Now, if we look at it in another way, we can see that the graphics is taking some power, media is taking some power, radio and the other applications like browsing and all those. Here also these things we can, so for each of them, we need powerful processing. Now, all of them, if I just make it in a single chip doing everything, single processor core, one core doing everything, then it will be difficult for me to manage the power of the individual segments. Sometimes maybe you are not running audio, okay? Sometimes you are not playing the media maybe. Then certainly what we learned is that according to whatever we have learned till now, that we can put the power off in that processor. Individually I can do that dynamic power management for that processor, which I could not do if that was a monolith, if that was a single processor. So, therefore, here also it is the same thing is being shown, and it is the data from the International Technology Roadmap for Semiconductors in 2010. The scenario is not very good, because you see memory static power is shown by the green, and the static power means the leakage current, right. Static power is the leakage current, dynamic power is our equation, that thing, switching current. Now, you see the static power, as you are pushing in more and more and more and more transistors, the static power is shooting up. By 2024 it will be, where are we now? We are now somewhere here, and this is the ideal that we can handle with the, I mean, so much power we can handle, we are already above that. Now, logic state power, let us see, stay in 2016, takes a certain extent. Memory dynamic power means what? What does memory dynamic power mean? The switching in the memory, I am accessing a memory and getting its data, that is taking up a considerable amount of power. And the logic dynamic power, means in the circuit, in the processor, wherever switchings are taking place. All of them have to be reduced, so that the entire thing can be pushed around this blue line. So, we are actually this in milliwatt. So, the prescribed wattage is 0.5 to 1 watt, and all of us, for small mobiles we are violating that, for large mobiles we are violating that heavily. So, more and more we go for the smartphones, and this we are suffering from that. We have to bring it somehow over here. So, what are the measures that people can take? But now, you see here the processor, we are showing the red parts are the ones which are right now consuming power, and some parts, say this application part, maybe I am not running, by our DPM strategy, dynamic power management strategy, I can shut it off. Okay. So, thereby we can have some parts, baseband part is on, all right. If it is a CDMA, broad DSM both, say I can put CDMA on, this can be on or off. I can put the real time tasks I am not doing, I want to put them off, and thereby I can measure the leakage current, etc. Okay. So, dark silicon, you can see this, right. So, now we have talked about different means. Now, the cyber physical systems or the embedded systems, in order to be efficient, there are so many parameters. We are not going to talk about the weight efficiency or the cost efficiency, that is a different aspect, although important. We are talking about the code size efficiency, because you see the code size efficiency is also important for the system on a chip. I cannot have enough, I mean as much memory as I like. Runtime efficiency for the speed and energy efficiency. So, these are the things. So, I will be talking about this, the way we can handle code size efficiency. We have shown some code size efficiency, or the VLIW was actually doing reducing the accessing and increasing the parallelism and pushing the overhead to the compiler. All right. So, in the next class we will be talking about the code size efficiency. We will start with that the next class, but till now let me quickly summarize what we have learned. Now, we have got two conflicting constraints. One is the performance, another is the power, and the way the methods that we have seen are voltage scaling. All right. The other one is dynamic power management, we put certain things off. Okay. The other thing that we have seen today is also, if we have got large instruction words, if we can reduce the number of memory fetches, memory accesses, writing into the memory, reading from the memory, then also we reduce power. Okay. So, we will take up the code size efficiency from the next class.